Yeah, that seems to work.
Everything's working. All right.
Okay, so
Karsten, everybody.
yeah, so I'm here to talk about Cartesi, which is an alternative RISC-V based virtual machine. And just to kind of like keep it short, maybe very short, the Cartesi machine is a RISC-V emulator. It runs completely deterministically. If you start out in the same starting state, you'll end up in the same ending state. It's what we call, let's say, general purpose, as in it implements the full RISC-V 64-bit GC, which means basically you can run Ubuntu inside it if you want to. It's one of those things that's written in C++. It's the LGPL licensed. It runs on Wasm. It runs on Linux. It runs on Mac. And as of a couple of days ago, it runs on MS-DOS, in case you actually wanted to have that. And one of the things that kind of comes with is that it comes with 64-bit memory addressability, which means that there's more than enough space in the virtual machine for you to do anything you could possibly think of. And it's one of those, it's been developing since 2018, and it's still being developed. One of the things about this virtual machine is that the entire state of the virtual machine is memory. It can be Merkleized, as in that you can basically represent the entire state of the virtual machine with a single hash. And you can kind of like stop and start it, you can persist it, you can snapshot it, you can roll it back. And that basically means that it's possible to use it in, for example, an optimistic roll-up kind of manner, where you kind of like getting to the point of disagreement and then running one particular step and proving to a blockchain, which then runs one single RISC-V instruction. And I'll build a little bit into it here. And it's kind of programmable. You can adapt it into even ZK environments. We have been trying to do something as crazy as trying to run Linux inside ZK proof using RISC-0 technology, where we basically stuffed our Cartesi machine, our virtual machine, inside RISC-0. And it takes 3 days to kind of ZK proof that you're booting Linux, but at least it works now, right? And basically, I think that the ultimate runtime, kind of like for application, is kind of like a general purpose processor virtual machine that can run the full 64-bit OS. And if you're interested to kind of see the source code of it or the white paper, this is kind of like the links you can go to. So why Cartesi? Why does Cartesi matter, right? And I believe it matters because it's less of a leap for most developers to actually jump into using using blockchain. If you know a bit of TypeScript, if you know a little bit of JavaScript, even PHP or something like that, you can start using Cartesi. Because why can't we actually go in and, let's say, develop application change just with the same mindset that we're approaching things like AWS, Heroku, or Vercel, and so on, right? And one of the things we kind of get for free also was mentioned in my earlier talk, that we get compilers, we get tooling, we get debuggers, we get testing frameworks. We don't need to reinvent this whole thing again. And at the same time, we also get to benefit from that. Well, people have spent the last almost 50 years improving these compilers, these frameworks, these libraries, et cetera, et cetera. And this is maybe a bit of a controversial opinion, but since we have a panel, I thought I might as well get to it, that I believe that if we're looking kind of like back at the EVM in the last like 5 years or more of the EVM, it has kind of like ended up with a trail of dead projects, dead languages, broken developer experience, and I kind of like believe that this causes basically a terrifying and heavy developer experience. And I think that it doesn't help because we also need to have not just completely specialized, almost high priest-like smart contract writers. We also need the average people, the people who want to build, let's say, decentralized message boards or other kind of like small things like this. And this is where I think that Cartesi fits in. Just go with it. I also think that us who's working in virtual machine business and roll-ups and so on, we have many shared challenges. Like, for example, how do we actually talk to each other? We have many different technologies. How do we communicate? How we bridge information between each other? Things about sequencers that are now becoming much more relevant with projects like Celestia and Espresso Sequencer. How do we build those kind of like virtual machine interfaces for block builders, for example, in publisher, proposer builder separation, for example? How do we deal with atomic cross-roll-up transactions in the same way where it doesn't become a frustrating experience for the users? How do we deal with the fact that, well, there's going to be just as many sequencers as there's roll-ups out there, or at least as many as it seems like with technology? Things about indexing, archiving, and also probably a problem that most of us share here. we are really the experts in making rollup or blockchain virtual machines, and there's really nobody out there who can actually really help us to audit it. So maybe we can start the practice of, let's say, starting to audit each other's VMs, et cetera, and things about, is there a way we can use restaking, eigenlayer to kind of like make things cross virtual machine more better, and about proto-dunk sharding, because there's not a lot of blobs available every single time on Ethereum, and kind of like topics that, for sake of collaboration, we can kind of like get to. And yeah, compared to many other talks today, mine is short. So if you want to talk more, you can poke me on Telegram, find somewhere with a Cartesi t-shirt, read more about Cartesi machine or about Cartesi, and that's pretty much it. Any questions?
Sorry? That's a great idea. Let's give a round of applause for Karsten. Any questions? He beat you to it. Sorry. I'll be right there.
Thanks for the talk. I wanted to understand what your system of proving inputs into the VM looks like. So say like the Ethereum virtual machine, or you taking like state from Ethereum, proving the correctness of that within a Cartesi VM?
So the way to kind of think about how input makes it inside a Cartesi machine is basically, you have the state hash, right? It represents the memory. What you basically want to do is kind of stitch the new data that comes in from the Ethereum, in this particular case, into the memory image. So you end up basically with a new hash of the machine state. So then basically everybody agrees on this is the starting state of the machine, right? And then we can kind of like replicate the computation. We can go in and let's say, if there's a disagreement about it, we can find out where did we disagree. But in general, it's just basically like writing into memory. And from point of view of the client, it's basically a JSON RPC call into the virtual machine, write this into memory, that's it. And get the proofs for actually doing so. Does that answer your question?
Yeah, hey, so what I was going to ask is, I really like the part where you told about collaboration, you know, so we have a bunch of VM specialists, and you also talked about doing Cartesi machine proofs using RISC-0, who are also here, so could you talk more about that?
Yeah, so if we're thinking a little bit about, like, it's completely crazy to start up a machine all the time and like booting up Linux and then proving basically the whole execution of that. Because most transaction processing that actually will go in this particular case is that I'll boot up Linux, I'll boot up my application, and kind of like something like AWS Lambda is doing, I'll snapshot at that point. I don't even need to, never ever need to prove that I booted up Linux again. So when I actually get a transaction in that I'm actually modifying, I can prove that tiny, tiny piece, which actually not that many kind of like full-blown general purpose cycles, and make a proof of out of that. So this is one way to kind of like bring, let's say, we don't need to reinvent the entire operating system, let's say, interface. We can go ahead and basically use what's already out there. Of course, as somebody said earlier, the more layers you have, the more probabilities of issues there are. But at the same time, we can also go in and now suddenly do things like, let's say, ZK proving that you can run an entire Rust compilation or kernel build. I have done, let's say, reproducible Docker containers with this. There's many, many interesting things you can do when you can actually have a full machine that's actually complete and can run Linux in it.
Hi, just to be clear, does the user boot up a Linux machine in their browser, computer, or is the sequencer basically a Linux machine?
Yeah, so let me take it from this perspective, right? Like the virtual machine doesn't really care about what sequencer is attached to, right? So it could be Expresso sequencer. We have recently done a demo where we put 17 megabytes of data through the Expresso sequencer, video decoded and showed it with ASCII art, and it happened to be the REC-row, right? So you can run the Cartesi machine in a browser if you want to. You'll naturally take in all the input to kind of like get to the same state, but in most cases, people will want to kind of like, you do it like, for example, it's Optimism is doing it at the moment, where you're kind of optimistically proving to the blockchain, this is the state after a certain amount of inputs. So this is what kind of like optimistic proving is about, right? That after, let's say, everybody has the possibility to dispute what the computation result is, if nobody successfully challenged it, it becomes the computation result. So it kind of depends on how long do you want to wait for the result. Of course, there's possibility to have something like, let's say that you have a node you connect to and kind of check what the latest state is, but there's kind of like also the possibility that these things might eventually also even provide ZK proofs that the execution was actually correct when you're querying about a particular piece of data.
So in the optimistic case, do you have race conditions wherein user A might have taken the current state of the blockchain, whereas user B asked a node which didn't fully know, hasn't sunk up yet, and both of them run their transactions on the same machine?
I don't think there's any, so this is replicated computing, right? So if you're a validator, you're able to replicate the execution completely. If you're dishonest, you'll try to modify it. Like, let's say that I'm getting $1 billion instead of you, right? But the blockchain basically helps ordering the transactions, right? And then basically the Cartesi machine, in this particular case, takes the transactions, runs them in there, updates the state of the machine, or updates some outside state of it, which, for example, could be an IPFS database or something like that. And so there's always an ordering, an exact, let's say, deterministic order of how the virtual machine is supposed to run.
All right. Karsten, thank you very much.
Yep.
Then our next speaker, Nick, CEO of Fuel. Give him a round of applause, please. I'll grab you the clicker.
All right. Some slippery stairs. All right, so I wanted to do a highly technical presentation describing every aspect of our register design, our memory, the way things work, the way calls work, the way fraud proving works, the way introspection works. But instead, I'm just going to tell you a story, and you can look that up later yourself, because I only have 7 minutes. So yeah, to start it off, if you guys can hear me okay. So the Fuel VM, what the hell is this? Basically, for today's agenda, we'll just go over some more burning questions that I think a lot of people have about what our VM is and how we've designed it. Starting off with UTXOs, then going over to how we do smart contracts and UTXOs, because that's always a big question. P2SH and predicates, and then as well how Fuel is trying to design the foundation for a more modular world for blockchain. So to start it off, the EVM is great, but very convoluted and really complicated. So it was designed, unfortunately, very quickly. And I know because I was sort of like at the aftermath of when they did it, and it was very fast. And unfortunately, it came with a lot of interesting baggage. While it served its purpose and moved blockchain forward tremendously, like I think we all know, we could probably do something maybe a little more interesting and probably try something different. So, so with Fuel particularly, a big thing to kind of think about here is basically like the power of some of the Bitcoin transaction model, but with really the expressiveness and the flexibility of Ethereum. So that's basically how you could think about the Fuel VM in and of itself. So fundamentally with UTXOs, it's a scary word, but really it's just to describe what we kind of consider as state access lists. So effectively just describing what areas of state you're touching in a virtual machine, and then basically describing how that's going to be changed. So like a typical model just has some inputs and some outputs, and basically each transaction is sort of defining a state transition, you could say. So just transitioning from the previous state where everyone had this to another state where everyone else had something else. So it's really quite simple. It's just the word, you kind of say it, and then you lose people. So to demystify it, it's really dumb and simple, and it's basically just this. So a really nice side effect and something that the Fuel VM tries to do is reduce a lot of burden that we have with blockchain, which typically comes from state growth. So if you know anything about how Ethereum's designed and how a lot of blockchains are designed, the state can be immense and enormous. And effectively, and I'll show you in a second, this really constrains our ability to sustainably scale as a technology and as a group. So blockchains that use a UTXO model can benefit from some really nice properties. One is, if you know anything about blockchains, it doesn't need to have a global state root, but it can still be valid and still like-client provable, which is a huge win if you're looking at how to build a blockchain. If you need to serialize every single state transition into a giant Merkle tree, it's really prohibitive, very expensive, and it's not great. So we remove that with a UTXO model, which is really cool. The second thing is UTXOs provide a state minimized alternative to smart contracts. So in RVM, we try to get developers to push away from using smart contracts, even though you have full, flexible Ethereum-style smart contracts. We try to give you more tools. And as well, each UTXO, when it's spent, only takes up a single state element. And again, it retains like-client provability. So this is a very, very important factor with blockchain design, and it's something that, unfortunately, many blockchains succumb to. So state reduction is a big piece, but I'm not going to spend a lot of time on it here. Tomorrow at L2 Day, I'm going to talk about how we basically solve or reduce the state growth problem significantly using this technique. But anyway, that's one big benefit. And as you can see, Peter, the developer of Go Ethereum, really doesn't like state and talks about it all the time, and basically says that, you know, if we don't deal with these kinds of things, we don't find other ways to address it, we're going to see an existential issue with Ethereum at their current node requirements. So in addition, the Fuel virtual machine is also designed for parallel processing. So this is a really important feature of, I would say, any modern virtual machine. And you really want to be able to use all the power of your machine to process transactions. So in a sense, UTXOs enable us to do this because they act as a state access list. So this means that, you know, you can analyze a block and you can just say, okay, I know these transactions are going to touch these pieces, and thus we can process them on these threads, and they're not going to bother each other. So very important. Second thing is, not only can you process in parallel within a block, but you can process across blocks in parallel too. So you get really nice properties in terms of parallelism with using a state access model like UTXOs. So in terms of the results, and I know TPS is a horrible number and we should never really discuss it, but fuck it, everyone asked me for the TPS, so I'm going to give you the TPS. So basically, the way to think about this is per core right now on an unoptimized node that we have, we can verify about 7,000 transactions per second. On an 8-core, up to 58,000. And because of the way our model's designed and also the way that UTXOs work, we're able to get really nice compression properties, which will allow us to post about 2,500 TPS a second on Ethereum DA, given that we used all the DA on Ethereum. But effectively, that's what we can process at the limit. And so effectively, large numbers, but again, TPS is a horrible metric, so don't ever use it unless you have to, unfortunately, just say it once. But anyway, there, I said it once. So in terms of another thing that's very, very important, so the Fuel VM also brings something that I think is incredibly important to the design of blockchains in general, which is very rich light clients. So light client support allows just regular people to be able to validate and introspect different pieces of the chain. So with Fuel, we redesigned things like the block header and the transaction structure such that it's very easy to introspect everything that's going on within the system, such that even on-chain light clients are very approachable. They're very easy. It's really just verifying a few light Merkle proofs, so it's nothing too intense. And so when you do things from scratch and you rebuild, you get to address and fix a lot of these shortcomings that you typically see in these blockchain systems. So rich light clients allow for really great cross-chain introspection. So effectively, one rollup can really take a look at what's happening in another rollup. And this is very, very important if you want to have really nice properties of bridging between rollups. So a lot of the Fuel VM design is designed to minimize state, and it's also designed to have really nice properties of introspection. So light data introspection is very important to us in terms of how this will work. And ultimately what this means is that bridging and doing trustless bridging with no multi-sigs and everything else is very, very approachable, even in the optimistic setting, without ZK, without anything complicated. It's just very easy to see what's going on all the time. Another thing that we focus on in our asset model in UTXOs is having multiple native assets. So with Ethereum, unfortunately, the only native asset is Ether, which is really, really constraining. Every other asset is at the application level, and this really constrains the kinds of designs that you can actually put together with, with a blockchain. So in the Fuel VM, all assets are, or can be, at the native level. And this allows for a really interesting property of settling lots of different kinds of transactions with lots of different assets and lots of different criteria for settlement. So everything coming off of exchanges really benefits from this because a lot of the time you just need to send asset here, send asset there. And that's a lot of what blockchain does. And so we really optimize for that in terms of our native model itself. And as well, this also means not only settling fungible tokens, but also NFTs. So this is another question we get all the time, which is UTXOs and smart contracts and how effectively this whole thing with Cardano really kind of skewed everyone's perspective quite a lot in terms of how this actually functions. But basically, a big thing that came up was Cardano designed this smart contract model that was really blocking in terms of how it was processed, and it ended up creating a horrible user experience, thus scarring UTXOs for the end of time for everyone else that actually doesn't have this issue. So if you ask, which was why I was particularly angry with Cardano people. Nothing against Cardano people. Just this was a bad design decision. Is it possible to have really nice Ethereum-style malleable state smart contracts in a VM? The answer is absolutely. And this is another funny one that I found too. But effectively, their scientists are working on it. Effectively, UTXO smart contracts are very possible. So you can see here the inputs act as a nice state access list. You have multiple inputs. One's a contract input, in this case how the Fuel VM works. And then when you're basically defining the output, you're notating two things, the state and the receipt route. But the user doesn't do that. The block producer does that. And so that gives you that malleability while still having all of the niceties of a state access list like system like Fuel. So yes, we can do Ethereum-style smart contracts, and again, state is malleable, et cetera, et cetera. And it supports all the things that you like about doing EVM-style smart contracts, but doing it in a way that, again, can be parallel processed, et cetera. So another nice thing that we brought over from the Bitcoin space is effectively a concept of spending conditions. And so pay-to-script hashes is something that Bitcoin had before because of its UTXO model. This effectively allows you to send assets to a script that's a spending condition. And with this, you basically are trading off using a smart contract and state for doing something more over bandwidth and just using something that's lighter. And in my presentation tomorrow, I'll go into why that actually fundamentally addresses huge issues of state growth and kind of blockchain I/O issues. But in this presentation, it's very good. It's very state minimized. The next thing is that this also acts as effective account abstraction. So with Fuel, you can sign at the native level with Solana wallet, with P256, with any kind of signing curve you want, and it's supported at the native level and fluently in a multi-actor transaction, which is very, very nice when you have lots of different people settling lots of different things. And the code for this is actually prunable, so it doesn't need to be stored. So again, it's very light on processing. And Fuel predicates are really our version of this pay-to-script hash idea. And so you have expressiveness, but we keep them basically atomic so that we can not only process the block in parallel, but we can process all of the predicates in parallel too. And so again, this powers everything. And it can not only do multi-sigs and native account abstraction, but it can actually also fundamentally do order books, which is very cool. So it's a nice side effect. So that will be the most state minimized possible order book you could ever construct. And again, each UTXO only takes up one state element. So in terms of improving on the existing blockchain stuff and moving it over into something more modern, Fuel really does the job. In terms of being kind of a foundational layer for blockchains and blockchain VMs, I know I've covered a lot of different things, but the main thing is that on the horizon, there's also a lot of stuff to look forward to. So native meta transactions, or in this case, like fee abstraction, so not having to be stuck with fees, but doing that in a very efficient way at the very lowest level will be very fundamental for Fuel. As well, things like ZK proving with UTXOs are much better in the sense that on the ZK side of things, you really want things to be more atomic, and that way you can do more parallelism with ZK itself. So I'm sure like Bobin and the Miden team will give you a good rundown of why UTXOs are a great model for that. And as well, UTXOs are also fantastic for privacy properties, and as well for settling from intents. So settling down from, you have a bunch of users, and they have a bunch of intents that they would like to eventually settle. The multi-asset model of the Fuel VM is very much like that. So that's basically it. And again, I would say that, you know, I could have talked about all the very detailed specifics of our VM and how it works in the word sizes and everything else, but I just wanted to cover more of the major stuff that people typically ask. And if you want to learn about how our register VM works or all this other stuff, just read the specs, because it'll be a way better presentation than I can give in 7 minutes. So, all right, thank you. Thank you, everyone. Yeah.
All right. Do we have any questions? Questions? Okay.
Nope.
Very straightforward.
Yep.
Okay.
Oh.
Oh wait, last minute entry.
Yeah, I was taking some notes while you were talking. So great presentation, Nick. Really quite impressed after we had a talk outside. You did mention something about having native support for particular signatures. Is that what you said?
Yeah.
And then you mentioned some of the signatures in Solana. Can you talk a bit more about that?
Yeah, so in terms of different native signing support, you kind of don't want to burden the user with having to switch wallets or switch keys. And so you want to support whatever wallets they have. So most people in the room actually have a hardware wallet that they're carrying all the time, and it's their iPhone typically, or Android maybe. And they actually don't need another hardware wallet for a lot of different cases. So being able to support that signing type at the native level is very important if we wanted to get, say, the whole room to adopt a new piece of technology. So in a sense, you want to support the signing technology that people have, and that could be MetaMask, that could be you know, like a Cosmos wallet, or it could be you know, just a hardware wallet that they have in their pocket. Yeah.
Interesting, because we also talked about having sort of native app chains that settle on Fuel.
Yeah.
Right. Okay. Got it. Great.
Yeah.
Thanks.
Cool. Any other questions? Thoughts? Nope.
So for the pay-to-script hash opcode, do you also support different kinds of hashing functions in order to enable atomic swaps and the other things with a wide range of other layer 1 blockchains?
Yeah, 100%. So within the predicate itself, you can tap into pretty much anything in the VM that doesn't touch state. So the predicate tries to remain a stateless, effectively atomic script. So hashing, all that kind of execution is fully available. The Fuel VM also has some very interesting properties of self-introspection. So in a predicate itself, you can actually take a look at the transaction itself, because it'll be put in memory for you. So these little things allow you to do really cool stuff. So you can introspect your own transaction, look at the inputs, look at any aspect of it, hash, verify, Merkle proof, whatever, and then that becomes your spending condition. So effectively, it's providing the developer more ways to do things that are outside of the context of smart contracts. Because again, you can do everything with smart contracts, but as some of the devs in the room probably know, it's absolutely horrible to try to jam everything through smart contract transactions. Like, it basically ruins all forms of scalability. So yeah, that's kind of the idea. So 100%. Yeah. Yeah.
I have a follow-up question. I think there's a lot of talk currently. There's like EAP 7212, I believe, which essentially talks about using SCP's 256R1, which is commonly used for biometrics and enclaves.
Yeah.
And I was wondering if you're looking to support that now that the industry is kind of...
I'm actually demoing that tomorrow.
Ooh,
Yeah.
okay, nice.
So, and we've supported that for a few months already. We just didn't write the WebAuthn script. So I spent the last few days writing that, and it was absolute hell. But we've got it running.
Nice.
got it verifying. Yeah.
Yeah,
Woo!
that's critical for onboarding, just in case you could essentially create a wallet using biometrics, and the user doesn't have to be exposed to their private keys.
Yeah, so that you'll have with full native support, and it'll also be tooled in our SDKs too.
That's huge.
Yeah.
Last context. This is pretty cool because currently in the Ethereum world, people are talking about implementing SCP-256-R1 on a layer 2 and then putting it on the layer 1. So while they're supporting it natively here. Cool.
Yeah.
Thanks.
Yeah.
All right.
All right.
Cool. Thank you, Nick.
All right, thanks everyone.
Thank you so much.
Be careful. Steps there. Can I have the clicker? Then I would like to invite our next speaker on stage, Raul from Offchain Labs. There you go. Thank you. And that one. Perfect. We do 6 minutes. Then you get 2 more.
Okay, great. Okay, hello everyone. My name is Raul. I'm an engineer at Offchain Labs, the team that is behind the Arbitrum Layer 2. And I'm also a maintainer of the Prism client, which runs Ethereum proof of stake today. So today we'll be talking about Arbitrum Stylus, which is a technology that we recently announced, and it's live on testnet. It allows developers to write Ethereum equivalent smart contracts in some of their favorite programming languages, and basically almost any language that compiles to WebAssembly, which is really exciting. So the EVM is, of course, meant to be small and easy to price. And the bytecode can be fairly small. It looks very transparent. It's simple. But of course, we've had so many developers adopt Solidity as the primary language, despite us having others such as Viper and such others that are coming up, such as Felang. And an unfortunate reality is that, of course, in the past we've seen situations where we would see DeFi hacks almost daily or weekly. And many of these are, of course, a result of the design decisions that came from implementing the EVM. But I'm not here to bash the EVM or say that we need to completely abandon it. Instead, we highly believe that the EVM is here to stay. And we know that the developer experience, the tooling that has been invested over many years, is only going to grow stronger over time. So instead of approaching the problem from the angle of, hey, can we just introduce something completely different, we think about it, how can we give existing Solidity and EVM developers more superpowers? And of course, many projects have introduced alternative VMs, which is of course the theme of the summit, many with success as has been demonstrated, which is awesome. But we believe the network effects are not going away, and there are network effects at many different layers here, right? So there are network effects at the tooling layer, at the application layer, in the actual VM layer, of course, and it's about which ones of these network effects do we want to maintain moving forward. So the question is, to be or not to be? Do we need to abandon it entirely, or can we do something better with the existing EVM? Today, Ethereum is its own little sandbox, kind of, developers have to write in languages that then compile into EVM bytecode. And we're leaving out a huge swath of developers that are already used to many existing programming languages and backend languages. So the answer, the question is, why not both? So introducing Arbitrum Stylus. So Stylus is a next-generation programming environment for Arbitrum chains. It allows developers to write Rust, C, C++, Zig, more, you name it. You can add support for it yourself. It's fully EVM interoperable. And of course, in the EVM, some benchmarks that we have is in the time that the EVM can do 7 single add instructions, with Stylus, we're able to do complete rounds of hashing in a simple hash such as SIP hash, but the benefits don't end there. Because Arbitrum today proves computation over WebAssembly, which is kind of the bytecode that we choose to compile to for many reasons, we ask ourselves the question, can we support execution of WebAssembly smart contracts in addition to EVM bytecode? And we believe that WebAssembly is really a powerful technology that will continue to shape the future. There's a famous quote that we like to look at from Solomon Hykes, the founder of Docker, that said that if WebAssembly and WASI, which is a standard library for WASM, existed, back when they were starting Docker, they probably wouldn't have needed to do that at all, which is pretty mind-blowing. So we call this EVM+. So one chain, multiple languages, fully composable, and it's not a new L2. We have one single state transition and one single state tree, which is the Ethereum state tree, one single database, and there is nothing like it. Stylus is much faster. Instead of being interpreted, such as the EVM is in many of the popular Ethereum clients, Stylus leverages some of the existing optimizations that exist for WebAssembly backends using the Wasmer runtime. So we have a 73x faster runtime against Kachak, for example. And surprisingly, some of the benchmarks around memory shows that Stylus can be 100 to 500x cheaper and more efficient in memory usage, even for medium or smaller size contracts. This slashes fees for users and enables things that just weren't previously possible. Examples are advanced cryptography, precompile research. Instead of waiting many years for Ethereum core devs to ship a new precompile, you can just do it in your own language and get all of that included, and also other heavy computation. What we're most excited about is that you can use the tools you're comfortable with, right? So you don't need to learn a brand new language. You don't need to learn our own DSL of Rust, if you say. Like you can basically do things however you do things today. If you want to access information about the EVM, we provide you with this syscall-like host set of functions, such as say access to storage, calling contracts, and you're able to write basically pure Rust code. And the most important part is that we have EVM equivalence in the sense of how we interoperate with the standards that exist. That means that developers or users could be talking to a smart contract with MetaMask or with their favorite tooling and not know that underneath the hood, it's written in Rust. And that contract is talking to another language that was written in Solidity. And that contract is talking to another one that was written in C. So we have an amazing level of customization and choices for developers to build upon these their own projects. As an example here, this contract is calling another one, and this is written in Solidity, but the one it's interacting to is in Rust. So there is no extra tooling required. It just works. We believe that EVM compatibility is not the ceiling, but rather the floor. Sorry, I think I messed that up, but anyways. Testnet is live, so you can try out Stylus today for yourself. We have documentation where you can start building, you can deploy some example applications, and really test out how different this is versus writing your own implementations in Solidity. The best part is that you can take existing projects, such as Rust crates or C projects, compile them directly, deploy them on chain, and just basically have that tooling available for you on Arbitrum testnet, which is really exciting. We have first-class support for Rust and C, and because the API to the EVM is so low level, anyone can write a custom framework on top of this. Anyone can write an SDK. It's permissionless. You can do it yourself. Some people started already writing, more C SDKs, and there is Zig SDKs as well available for people to use. We also have examples of Ethereum standards, such as ERC20 tokens, that are implemented with Stylus and have EVM equivalents at the storage layer and at the ABI layer. So you're able to interact with them, mint them, transfer them any way you would, and this contract is written in Rust. That means you can see transactions in Etherscan, you can see that it emits the same events that an ERC20 token in Solidity would, and all of that is available to developers right off the bat. If you want to add other programming languages, it's super easy. Adding support for Zig, which is a brand new, relatively brand new language that is aimed to be a successor to C, took me around 16 lines of code. And anyone can do this. So you can even write your contracts in assembly script, or you can do it in a functional programming language, if you will, and you can deploy that to Arbitrum Stylus. And there, the sky is the limit. Do you need something low level? So Stylus provides a very low level entry point, which is just bytes in and bytes out. And you can get started and just go wild. You can do anything you want here. Some examples, there are some benchmarks of showing hyper-optimized smart contracts in Yule, for example, for EVM bytecode, and running a similar non-optimized version of a contract in Rust. And Stylus really does shine the number of iterations, and the more expensive the computation becomes. Moreover, Stylus programs can export ABI interfaces that are Solidity equivalent. So in this example, I deployed a BLS signature verification contract in Rust, and I'm able to call it using the Solidity interface, and opens up a ton of opportunities at the application layer that just weren't there before. We also have developer tutorials, so we have a lot of information. And all you have to do is navigate to arbitrum.io/stylus. And here's a capybara. Thank you.
Thanks, Raul. Don't go yet, don't go yet. Maybe we got some questions. Yes, sir.
Yeah, hey, so very nice. I have a question about metering. So how does metering work on Stylus, essentially? Thank you.
Oh, sorry, can you repeat that?
Metering, like
metering, gas
gas
metering. Yeah, that's a great question. So a big challenge of dealing with WebAssembly is how do you effectively meter the computation in order for, to appropriately gas price things. So of course, gas metering is different than the EVM gas model. We have done a lot of metering on a lot of benchmarks to better understand how to price each WASM opcode. But Stylus actually does a lot of cross-checking. It does depth checking. It does memory checking. It does stack overflow checking. And we basically walk the contract bytecode that you deploy. We sanitize it, make sure that it matches all those items before it can be deployed on chain. So we have a very strong set of checks, unbounded execution, of course, and we feel confident that this is something that that we have figured out. So. Yeah, and you can look at our metering code and middlewares as well. It's all open source. Yeah.
Any other questions? I could have stayed where I was.
Hi, great presentation. WASM is known to be quite hard to deal with in terms of error handling. I'm curious, like EVM, a lot of reverts happen. Has it been a pain to handle reverts for Stylus, and how did you do it?
Yeah, excellent question. So the nice thing about Stylus is that you can run your Rust code as a normal Rust program, and you can probably inject it with a backend. So you can use some interface. We plan to support things like Foundry, like Forge, and Ganache, and things like this. So from there, you'll be able to easily do that. So you can run it as a native binary, or you can run it as a WASM binary. It's really helpful to run in native mode for debugging, but in WASM, if you use the Stylus SDK, we support the Solidity ABI model, we support Solidity storage types and everything, so reverts and execution debugging will be very similar to your Solidity debugging experience. And we hope that with tools like Foundry, you'll be able to just debug it like you would any normal smart contract. Yeah.
So, quick question. So this would still work with Solidity-based proxies, right? I would be able to deploy this and point my regular, let's say, Diamond proxy to use this as a facet, right?
Yes, that is correct. That's a very exciting use case. So you can swap out something that's in Solidity and upgrade that to a Rust contract, and it will be equivalent.
Then I got one more question for you.
Sure, yeah.
Hey, it's me again. Can you hear me well?
Yes.
Yes. So I'm also wondering about standard library support, like for example in Rust. Can you code using the standard library, or would you need in Rust to use no STD or something like that?
Yes, you can use the standard library. Of course, you can't use things that are non-deterministic. You can't. Floating point support is coming, so that's going to be a big thing. And yes, you can use the standard library. You can use it with no standard library, which is really exciting. Something that we think is really powerful is that somebody could deploy the Rust standard library as a standalone thing to Arbitrum Stylus, and then programs could link against it, kind of like how they, how we do dynamic linking and linking in general in the Solidity ABI model. So. That's a possibility for sure.
All right. Thank you, Raul.
Thank you.
Thanks, man. And our next speaker is Bobin from Polygon. There you are.
Thank you. Hey, everyone. Very excited to be here. All right, so my talk today is about Miden VM. This is the heart of Polygon Miden rollup. I will actually not talk a lot about the actual rollup aspects of this. Polygon Miden VM is kind of general purpose, and you can run many rollups with it. The way it works actually is like you can deploy different OS on this, and the OS defines what the rollup is. So like things like UTXOs I'm very excited about, but they're not actually encoded in the VM itself. This is something that could encode in the OS that runs on it. And so like Polygon Miden OS, the one that runs the rollup is the one that determines like the structure of the rollup and all of that. But I did, before kind of going into details of Polygon Miden, I want to give an introduction of what the ZK VM is, and probably it's familiar to most of you, but I think it's good to set the context. So let's start with a regular VM. Regular VM basically is just a state machine where you start with some state, you apply some program to the state, you execute something, and then you get the output state. This is like a very, very basic thing. With the ZK VM, we get a couple more boxes here. So one of the boxes is you also get the proof of execution at the end. So as you execute some program, at the end you get this proof, and nobody else needs to execute this program again. They just like verify the proof and know that this set of inputs, if you apply this program, will lead to this set of outputs. The other thing that we get is that something called witness or private inputs. So you don't have to necessarily, it could be private data that you don't want to reveal, some secret to whoever needs to verify the program execution, or it could be something that you use for compression. As an example, you can probably, let's say this is a transaction that you are executing, and as part of the transaction, you need to verify a signature. So one of the nice things is that you could provide transaction or signature as part of the witness, and then nobody else needs to like actually verify the signature. They just verify the proof. Signature is already verified for them as part of this proof. And then, we can do some kinds of optimizations. We like frequently don't actually need to provide the full set of inputs and the full set of outputs as part of the inputs or even the program itself. We just provide commitments to the inputs, to the outputs, and to the program, and provide the actual state, the input and output states, and the program code via this witness. This allows us to compress things even more, like you only provide 32 bytes for a given program, for example. And that's, that describes the entire program because everything else is provided non-deterministically through the witness. All right. One very important aspect is proof is very fast to verify. It doesn't matter almost how long the execution takes of the actual program. The proof takes exponentially less time to verify. It takes much more time to create, so like the proving is costly, but the verification is cheap. So you can run the VM for 1,000 cycles or for 1,000,000 cycles or even maybe for 1,000,000,000 cycles, although for that you need a lot of memory. But let's say, regardless of how long the actual execution takes, the difference in verifying the proof is going to be very small. Like you could verify one proof in 1 millisecond, the other one in 2 milliseconds, and maybe, like the other one would be in like 2.5 milliseconds or whatever. So it's like really talking about milliseconds here for verifying almost arbitrary length computations. All right, one of the things that we want to answer, like when we build a ZK VM, or I guess any VM in general, is what instruction set we want to support, what we're going to want to go with. So like one option is like choose something mainstream, RISC-V, or you can choose WebAssembly. The other one you can say, we're going to be EVM equivalent. And then the other one is like we can build something that's ZK optimized, or you can say maybe specifically optimized for some other use case. And then there's a set of trade-offs that come with each choice. So for example, if you choose tooling, if you go with something that is mainstream, you have a ton of tools available. There is like, for Rust, WebAssembly, RISC-V, you have the entire tool chains built out already. If you go with EVM equivalents, you have already a lot of tools. Like it's not as many or it's not as rich of an ecosystem as for traditional languages or widely adopted languages, but it is, it's there. You have Foundry, Truffle, whatever, like a bunch of different tools. And then if you go with something that you build yourself, obviously you have you have to build everything from scratch. The other one is like, do you go with something that is blockchain focused? And this is like an interesting thing because, if you go with RISC-V or WASM, this is obviously not blockchain focused. You need to do extra things to make sure they work well in the context of a blockchain. There needs to be some modifications. If you go with EVM equivalents, obviously this is already blockchain focused by definition. And then if you're building your own thing, you can also, define like the parameters and make it blockchain focused as much as you want. And then this is specifically performance in the context of ZK, how easy it is to generate proofs. So for mainstream, it depends on which instruction set you go with. For something like RISC-V, maybe it's more efficient. Like if you try to do x86, it's like going to be very inefficient. RISC-V may be a bit more efficient. WASM is somewhere in the middle probably. But generally, those instruction sets were not built for ZK friendliness, so it's going to be a bit more costly to generate proofs. EVM was not built for ZK friendliness, and at Polygon we have ZK EVM, which does generate proofs, but it is, obviously the computations are costly, so it's not something that you would be able to run in a browser or on a mobile device, at least not anytime soon. And then lastly, if you're building your own instruction sets, you're free to optimize as much as you want. All right, so a quick overview of Miden VM. So first, I want to say, what are the things that we wanted to achieve with Miden VM? So first, kind of table stakes in a kind of smart contract world or regular world, but in the ZK, it's a big deal. Like build something that is Turing complete. Basically, you can execute any program. Frequently, especially in a circuit model, you're limited. You can't execute arbitrary programs. You have to account for the upper end or whatever, the worst case, and then you build your circuit for that. But we wanted to have something that is Turing complete. The second one is we want to have something blockchain focused. So we designed ISA specifically that targets use cases or optimizes for things that are relevant for blockchains. And I'll list some of the examples later, I think. But one of the things like verifying Merkle proofs should be efficient, hashing should be efficient, like some certain operations should be efficient, and so forth. So we gave priority to those. We built this for ZK friendliness, so we designed specifically the instruction set and operations so they can prove them easily in the ZK context. Our proofs are very efficient. You can execute. I mean, I'll show some performance numbers. The ZK VMs are still much slower than regular VMs, but as far as the ZK VMs go, Miden is pretty efficient. One of the core goals for us, and this also will bleed into the next point that I'll make, is safe composability. What I want to mention by this is that you can execute untrusted programs. So, and actually let me show the next one. So we want to have, one of the goals for Miden rollup, and therefore it bleeds into Miden VM design, is that we want to have privacy. And to have privacy, you need to execute programs that the blockchain operator or the block producer does not have any concept about. They are private. People kind of define them and just put a commitment on chain. So you need to be able to execute programs that are not known, or at least verify their execution. And therefore, we want to make sure that you can compose programs that you have no idea what they do with programs that you do know what they do, and it doesn't break anything. Like you don't write in the wrong place in the storage, or it doesn't break some invariance. So very important part of the Miden design is the safe composability, where you have execution context and you can execute something in a private context, and then it can have some interface to the public context and so forth. So that's one of the main design goals. To go over some high-level components, and I'm not going to go too much into details, but Miden is a stack machine, so you have an operand stack very similar to EVM. It has its pluses and minuses. Register machines are more efficient in some ways. Stack machines are easier to encode instructions. In the ZK context, there's other options, but we decided to go with a stack machine. We have memory, read-write memory that is accessible. Again, not a big deal for your usual machines, but in the ZK context, sometimes you could implement write-once memory, and it's much more efficient for ZK context. This is read-write memory. It's a bit more constraints, a bit more complicated, but we decided that it's needed because people are more used to this memory model than to a write-once model. The other thing we did is, we have this set of chiplets, and this is important if we think about circuit versus VM-based execution in the ZK context. Circuits are going to be much more efficient by design because you only create a circuit for what you need. VM, you have some overhead, but the way you deal with overhead is you create these chiplets that is a specialized accelerators for specific circuits, and you can accelerate hashing, you can accelerate signatures, and so forth. So we have a set of chiplets that we expose in the VM. And then one other cool thing that we have is that there is an interaction between the host and the actual VM, and the host is an environment that you can define as part of regular kind of computer or whatever that you're executing a regular program. One nice advantage of ZK virtual machines is that you can provide this non-deterministic inputs via the host. So you can offload a lot of computations to the host. And what I mean by that is if there is a computation that is much more efficient to verify than to compute, then you can perform the actual computation in the host and then ask the VM to verify it. An example of this could be like square root, for example. Square root by itself is a fairly complicated computation, but you can compute square root in the machine code very optimized and then give the result back to the VM, and the VM just needs to do a multiplication to verify that square root was computed correctly. So that allows us to simplify a lot of computations. Okay, I'm going to skip this. I think this is one of the things I want to cover. So we want to have Miden VM to support many different languages. The way we've designed this is that we have Miden assembly, and there is a Miden assembler that does it, compiles Miden assembly to kind of the code that gets executed in the VM. Miden assembly is not pretty to write in, like it's not nice, and we don't want people to do it, so we're building a tool chain. For example, right now we're building the compilation from Rust, so we want people to be able to write Rust, compile it to WebAssembly, and then WebAssembly gets compiled to Miden assembly, and that gets executed on the VM. We already kind of have a compiler working from WebAssembly to Miden assembly. We're still working on the Rust part. But we want to make it more general. There is actually other languages that we could plug in. Like I'm a big fan of Sway language, for example, and I would love it to also run on Miden VM at some point. And you can plug in there, like if you can compile to WebAssembly in specified format, you will be able to execute it on Miden VM. If you can compile it directly to Miden assembly, there's actually intermediate representation that I didn't show that is kind of crane lift based. You can compile to that, and it also will be executed by Miden VM. So we want to be support many different languages on Miden VM. And yeah, I'll skip that one because I think I'm out of time. But this is kind of performance, and you can see that it doesn't run that fast, but it is good enough to generate most transactions, and then we're working on optimizing this. All right. I think I'm out of time. Thank you.
Thank you. Do we have some questions? If not, then you can just keep talking. Okay.
Can we compile circum circuits to this?
It's not designed for that. You would not necessarily want to do circum. So the whole idea of the VM is that you don't need to design circuits. So I would say you would either do circum circuits or you would use Miden or something like that, because those are two alternative paths. Circum, I mean, you could do it. It probably would not be the best idea to do it.
Any other questions? We should just get you your own microphone. No?
So quick question. So if you go to slide one slide back.
Let me see.
Okay. So
I don't know.
No worries. So my question, because Polygon also has a ZK VM, right?
Yes.
So what's the performance gap between, because you're building a next ZK VM. So what's the performance delta in there?
So so the applications are different, and the kind of execution models are different. So ZK VM, you are expected to be executed on a big server. So like right now, we are running ZK VM on a server with 128 cores and half a terabyte of RAM and things like that. So this is the purpose, how you would run ZK VM, because you have the 256-bit arithmetic to deal with, you have catch-ups and all of that stuff that is not very ZK friendly. Miden is designed to be run basically on a laptop or a smartphone. So right now we can run most transactions for Miden on a simple laptop. We estimate that for most transactions you probably don't need to have more than between 4 and 8 gigabytes of RAM to execute them. You should be able to do it, at least for now, on a let's say 6 or 8 core laptop. You should be able to do it in under a couple seconds. Again, it's not quite apples to apples comparison, because you can say, okay, well, what if I break out EVM transaction to be a single transaction, try to execute it? Maybe it would be 10x less efficient, but you can do it with EVM, because EVM is a global state, and that's part of the UTXO. You can't individually prove every EVM transaction and then combine them together. You have to have a single block that, because of interdependencies between transactions. Miden is slightly different, where you can execute each transaction individually, and it should be our goal is to do it. At least for now, you should be able to do it on a laptop, and maybe in a year or two, you should be able to do it on a smartphone as well. You combine them using recursive proof aggregation. Yeah.
I got one more question for you.
Yes. I have a different talk at a different event where I explain how that would work.
Quick question. Is this a, can you illustrate the difference between a Miden and Polygon Zero?
Well, Polygon Zero is a prover, right? So Polygon Zero is a prover that we're building for the POS chain. So they're different. So Miden is its own VM. Polygon Zero is the proving system, like Plonky 3, for example, which Miden may, probably will use in the future. So they're kind of different parts of the stack, so to say.
But the Zero can, be used to prove Miden as well as the Hermes.
So Plonky 3 we would be able to use Plonky 3 that is developed by Polygon Zero to prove Miden execution, same as EVM execution. So it's the backend prover that is responsible for actually generating proofs. It's not the instruction set of the VM. So you could use Plonky 3, for example, for proving EVM or proving Miden and whatnot. Miden is like a VM that rides on top of it. So Polygon Zero, it's not its separate VM.
And maybe just sort of a general question on Polygon, but you've got all these different solutions out there. How are they supposed to all accrue value to the Matic holders, token holders, if you will?
Yeah. So I mean, we have this vision of unified kind of ecosystem of chains, where you can run different chains. Like Miden would be one chain, zkEVM is another chain, POS, and then other third-party chains, so to say, that can plug into that. All of them will use some part of there's staking hub through which people may choose to validate or add security to their chains, or there could be some fees that depending on which parts of the security model you use, you could contribute to the kind of Matic and things like that. So through that aggregation, Miden doesn't have its own token or anything. So through that kind of aggregation, using shared proving and shared how should I say, staking kind of hub, that's how it will accrue back to Matic.
Thank you, Bobin. Give him a round of applause, please.
Thank you.
Thanks, man. Yes. Then I would like to invite on stage our last speaker of the day, Raul from Aztec.
All right, how's everyone doing? I know we've had a lot of talks today. I know there's meant to be lightning, but we're in Istanbul. It's kind of raining. We're here for a crypto event. So what does lightning? Well, if the speaker works. So what does? What's happening? Is it working? Not really. Can we go to the next slide, if it's possible?
I think you're holding it upside down.
That would explain a lot. All right, so what does lightning actually mean? Well, apparently, if you hear a thunder crash, that means VCs are getting wrecked. And if there's a lightning strike, that means it's time for you to ape into DeFi protocols. And storm clouds means there's a lot of liquidity pools that need funding. All right, I didn't have many memes, so I wanted to do something fun or dumb. So this was it. And I did lie about not having memes. This is my final one. Basically, I am working as a protocol engineer and a product manager on the Aztec rollup that we are building. Aztec is a privacy-focused, privacy-centered first rollup. And unfortunately, that meant we had to let go of EVM and build our own kind of rollup architecture. But what exactly is Aztec? Over the last few years, some people have called up a public-private ZK rollup because we have a private state, but we aren't just a private rollup. We also have the public state, just like you have on Ethereum. We're called a hybrid ZK rollup because we have both things. We call the ZK rollup because we're a ZK rollup, like Scroll, Starkware, etc. But we do another round of ZK to enable privacy at the user level. Some people decide to call us an actual ZK rollup because in a normal ZK rollup, you don't actually hide much information. It's still kind of transparent. Others call us an encrypted ZK rollup, which is an easier way of understanding how we enable privacy. But how does this public-private blockchain kind of work? Because we have a lot of blockchains today that are private, but very few that can do both. Like I think Nick said from Fuel, at the private layer, we use UTXOs, so Merkle tree of notes, as we call it, basically UTXOs. And all of those things happen at the user level, whereas on the public side of things, we have private state, public state. The public state is kind of like Ethereum in that you have an account state tree model, so a giant Merkle tree that just stores everything, which is kind of similar to Ethereum, right? And of course, because we are a rollup, we can do L2 to L1 transactions just like you expect from a normal rollup. Now, I've used the word rollup a lot, but I haven't said where we are, what you can do with it. So 2 months back, we announced the Aztec Sandbox, which is live today. It's a local developer environment, like a Foundry, an Anvil, a Ganache, if you will. So you can just run the entire rollup infrastructure locally on your machine and start playing and understanding with this new era of blockchains that we are considering, where you can have privacy as well as transparency and combine all of them to enable this new kind of architecture. Just in the last 2 months, we've seen hundreds of developers and companies already building on us. And we have a lot of dedicated feedback partners that are helping us think about new standards, new ways of building things. But what exactly can you build? What are these features of this new fancy virtual machine or blockchain that we're building? One of them, as I've said, public state, public functions, but also private functions. So in the private function domain, the way you can think about it is a transaction might happen in the blockchain, but the only thing you'll know is that something happened. Or more clearly, someone did something in some state at some function of some contract. Privacy. On the public side, it's kind of like Ethereum, right? So you create your intent, your transaction, you send it to the sequencer, and then, again, because you're a ZK rollup, the sequencer would execute the function, and then they prove it, that they did it correctly. But the best thing about all of this is actually not just having private functions and public functions, but having composability. Having private functions called public, having public called private. This lets you interweave both of the states. This lets you do many cool things. For example, if you're using Uniswap, you kind of want to know how much liquidity there is. You kind of want to know how much the volume is. That stuff should be public. But what you want to do should be private. So you can't just operate in a complete private model, which is why we have this seamless composability. To give you another example, MakerDAO works on liquidations, right? To liquidate, you kind of need to know the price that someone put in or how much collateral they put in. That's why you need both private state but also public state. Similarly, on that note, you could also read historic public data. That changes the ways people can think about airdrops. For example, you could prove that at certain block X, you had a certain NFT all embedded into the blockchain. You don't need your own database. You don't need to write SQL queries. It's all a part of the blockchain itself. We also have account abstraction. Account abstraction is a bit of an overloaded term right now, one of the biggest buzzwords, I guess. What we mean by that at Aztec is you're not going to have any externally owned accounts. Everything is kind of like a contract address. There's no real differentiation between the two. But that also means you can add any kind of signatures that you want. You could do Face ID-based signatures instead of having seed phrases. You could also just have seed phrases. In fact, you could also have nothing. So like, you could just have a dummy account, just like signs whatever, without any encryption. You can play around with all kinds of things that you want. My personal favorite feature, though, is this thing called portals, which is, so you have a lot of, everyone knows about DeFi Legos on L1. Everyone knows about Legos in the similar way on L2. But we've not kind of seen Legos across L1 and L2. What I mean is, imagine a world where you could like submit a collateral of ETH on L1 and just mint DAI on L2, or do the reverse. Imagine a world where you could supply on L1, borrow on L2, and then kind of have composability across them, right? So you have arbitrary message passing that executes things on L2s. We have our own kind, instead of like not having approvals at all, there are sometimes approval is useful. So we have our own way of implementing that kind of short circuit some of the issues of approvals that we've seen on L1 over the last 5-6 years. And finally, as I said about historic trees, you could also have encrypted or unencrypted information sharing. This is very useful when you just want to pass data to someone but don't want anyone else to know about it. And the way you build all of this is using our language that we call Aztec Noir. Some of you might be familiar, but Aztec is known for creating a ZK language called Noir, which is just a way for you to write your own ZK circuit. We have created a framework on top of that to create a smart contract language out of it. So if you're familiar with ZK circuits, notoriously hard to write. Everything in Aztec is kind of like a ZK circuit. Now it's no more with Aztec Noir. It feels like you're writing a normal language. You don't need to think about weird ZK abstractions. It just kind of works in the same way Sway or Solidity or other languages would work. Finally, Aztec will launch decentralized. That means decentralized sequencers. That means decentralized provers. That means upgrades where multisigs don't actually control your funds and can't just run away if they have to. That's all. We're at the first step with our local developer environment called Sandbox. We're looking for people to build with it. We're looking for people to help us think about some of the open issues we have. You can find me on Twitter, or you can also, sorry, X, or you can find our docs in GitHub. Thank you so much.
Thank you, Raul. Before we move on to the panel talk, we got time for one question. Then, just in time, sir. There you go.
Yeah, I wanted to wait. It's a tough question. Are you concerned about regulation around privacy?
So Aztec is going to be a censorship-resistant, privacy-first layer 2. The point of blockchains was to be completely decentralized, just so people can do what we want. And for that, you need to be fully decentralized, and it only makes sense to be censorship-resistant. So we are doing this not necessarily for regulatory environments, but because we think rollups should just be decentralized. And we think if you're fully decentralized, censorship-resistant, people can do what they want. But also if people, you can see all flavors of things. If you want, you can finally have regulations such as KYC that can be private, encrypted. So like that's something we haven't been able to do in blockchains because they're completely public, right? Now you can. You can store your personal data completely privately and still have whatever regulatory environments you want to be in.
Thanks.